Okay, and then all right. So in the last lecture, we talked about CMF, cumulative distribution function. So CMF, it is denoted with capital F, right? Unlike PMF. So remember, PMF was denoted with small f, right? And the camera example that we mentioned is a good example to, relate what does X mean. So basically, X, for example, is the number of cameras whose flash doesn't work, right? Or consider an experiment where you are rolling a die 5 times, right? And assume that in this experiment, you're setting X to be number of times you roll a 6, right? So the number that you get after you roll the die is 6. And I mentioned that we roll 5 times, right? So X here is a random variable, right? Because if we roll the die 5 times, X can be 0, meaning that we don't roll any 6. X can be 1, 2, 3, 4, or if we are very lucky, X is 5, right? Every time we roll, we get a 6, right? So basically, that's the concept of random variable. When we are doing an experiment and the number of, we are interested in some number, right? So f of X is
Professor?
Yeah, go ahead. Yeah, go ahead.
Sorry, just something about CDF and PMF quickly.
Yeah, sure.
Both of them can take discrete and continuous random variables, or is there a specific one for both?
Yeah, so in this chapter, X is always discrete, right? So X, for example, is the number of times that we roll a 6. So in both of them, X is actually, that's an excellent question. So yeah, so here X in PDF, X is a discrete random variable. So the numbers are 1, 2, 3, 4, 5, right? But you're right, actually, here X becomes continuous, right? Because very soon I'm going to plot, values of X. So in here, X is discrete, but here X becomes continuous. Did I answer your question?
Yeah, I think so. Thank you.
Yeah, so in this chapter, we talk about discrete random variables. So X here is discrete. So f of X is for discrete X. In the next chapter, we talk about X being continuous. So in that chapter, f of X is for continuous X. But in both chapters, when we talk about PMF, capital F of X is for continuous X, because PMF is defined for continuous X. So we will see the shape of CMF here is basically, it has a discontinuous shape, right? Because our X is here is discrete. So it has a discontinuous shape. In the next chapter, f of X is continuous. There are more people who have joined, so let me try to admit the new people. Okay. All right. Okay. So yeah, we lost the note. That's the disadvantage of admitting new people. So basically, think of X as the number of times that you roll a die, right? So we define capital F of X as cumulative distribution function. So the definition is basically clear from the word cumulative. F of X is equal to P of X being less than X. Or in other words, the sum of F of X's, the sum of PMFs, probability mass functions, when Xi is less than X, right? So if we look at the example that I just mentioned, we roll a die 5 times, X is defined as number of times 6 is rolled, right? So, so basically, in this experiment, X can be 0 all the way to 5, right? So f of X means P of X less than X, right? So for example, oops, sorry. So for example, what's going on? So for example, f of 2 in this experiment means probability of capital X less than or equal to 2, right? So that's the definition of PMF, and that means probability that X is equal to 0 plus probability that X equal to 1, X is equal to 2, right? So right now we can't really, I mean, we can compute them, but it's going to take some time. Like this one's actually easy. We can compute this one quickly, but for these, I'm going to give you some equations. So we are going to discuss how to compute it, right? So if you don't know how to compute P of X equal to 1 and P of X equal to 2, don't worry, right? You can, if you really think about it, there is a way to compute them, even with the equations that we know, but it's a little bit tricky. So for now, just let's say that f of 2 is equal to P of X equal to 0 plus P of X equal to 1 plus P of X equal to 2, right? So CMF has these 3 properties. The first property says that f of X, basically that's the definition, is basically sum of probabilities less than or equal to X, or the summation here of basically PDF. The second property says that the CDF, cumulative distribution function, or CMF. So I basically use 2 phrases interchangeably because they are, I mean, they are just quite close to each other. One is defined for discrete, one is defined for continuous. So CMF and PMF. Here M stands for mass, and these are for discrete, right? And we have 2 other phrases that are called CDF and PDF. Sorry, PDF, right? And these are for continuous case, right? But since the math is cleaner for the continuous case, these are more popular phrases, right? CDF and PDF. So because of that, I often use the word CDF and PDF, even though sometimes I have to use the phrase, even like in this slide, I should have used a cumulative mass function, but I use a CDF. It's not really important. You can use either word that you want. Okay, so the second property is that this basically CDF is between 0 and 1, right? And the reason for that is that this CDF is the summation of probabilities. And first of all of these probabilities are positive, right? We can never have a negative probability. So this is more than 0. And this is also less than 1, because remember, one of the axioms of probability says that the sum of all possible outcomes is 1, right? So if we look at the all possible outcomes, we are going to get 1, right? So in other words, it's always easier to think of an example. So f of 5. So what is f of 5? If you want, you can unmute yourself and answer. Anybody knows what is f of 5?
It's f of x equals 0 plus, sorry, p x equals 0, p x equals 1 till p x equals 5.
Exactly. So p of x. And what is that?
P of x less than or equal to 5.
Yeah, but what is like in terms of number? Is it like 0.5? Is it 0? Is it 1? Is it 10?
Is it 1?
Exactly, it's 1, right? This is one of the axioms of probability, right? Because if we add up all possible outcomes, we must get 1, right? So even before computing, we don't need to really compute these because this is the sum of all possible outcomes, right? When we roll a die 5 times, X can be 0 or 1 or 2 or 3 or 5, right? So if we add all of these up, we get actually 1, right? So f of X can never be more than 1. Right. And the third property says that if y is more than x, then f of y is more than f of x, right? So this has a mathematical name of this is that we say function f is monotonically increasing, meaning that it always goes up, right? It's impossible for f to go down, right? So this is an unacceptable f of x because f of x in this region is going down, and that's impossible, right? And the reason for that is that basically it's because of the definition of f of x, right? So if you look at f, so imagine that somehow you had an f of x that looks like this, right? So what that means is that in this region, right? When we add probabilities, the function decreases, right? So that means that those probabilities that we added up, they were negative because that's the only way that f of x can decrease, right? So I'm assuming this is f of x. And basically this is impossible because we know that small f of x is positive, right? So it's impossible for capital F of x to decrease. So if y is more than x, then f of y is more than f of x. Or if your calculus is very good, we will see in the next chapter that capital F is integral of small f. And because small f is positive, that means that f of f always has positive or 0 derivative, right? So the derivative of this function is always positive or 0. Because of that, we call it monotonically increasing. All right, so let's look at an example. Hopefully these math concepts become more tangible for you. So a day's production of 850 parts contains 50 defective parts. 2 parts are selected at random without replacement. Actually, I see more people have joined, so let me meet the new people. Okay. So we have 850 parts. I always like to draw basically a summary of the question. I encourage you to do the same. So we have 800 non-defective and 50 defective parts, right? And the question says 2 parts are selected at random without replacement. Let the random variable x be the number of defective parts, right? So basically, since we are selecting 2 parts, x can be 0, 1, or 2, right? Either we have 0 defective or 1 defective or 2 defective. Find the cumulative distribution of x, right? So basically what we have to do is that we have to find f of 0. So first I'm going to find PDF, sorry, I have to find PDF. So f of x equal to 0 is equal to p of x equal to 0, right? And that is going to be, so basically when I'm selecting 2 parts at random without replacement, I want none of them to be defective, right? So that means that I want the first part to be non-defective, so 800 divided by 850. And I want the second part also to be non-defective. So remember, once I remove the first part, here I have a total of 849 parts because I have removed 1 part already, because the question says it's without replacement. So basically I have 1 less part, and I also have 1 less non-defective part. So 799, right? So basically, to write this equation, I used the basically. Let me basically clarify what I did here. So basically, I said P of x equal to 0 means that P of first non-defective and second non-defective, right? And that is equal to, so and always means, sorry, and always means intersection, right? So it's basically the intersection of this and this. And for this, I'm using P of second non-defective given first non-defective times P of first non-defective, right? So P of first non-defective is here, 800 divided by 850, and P of second non-defective, given that the first is non-defective, is this other guy here, right? All right, so we calculated f of x equal to 0. Now I have to calculate f of x equal to 1. F of 1 is equal to P of x equal to 1, right? So now this one is a bit, I mean, it's not more difficult. It's just that it has two terms, right? So when I have one defective, what was x actually? Oh, I think yeah, so that's correct. Yeah, so x, I thought I made a mistake, but I didn't. So x is the number of defective parts. And in the previous case, x was 0, so both of them were non-defective. So that's good. Now for the second part, I have one defective, right? So when I have one defective, either the first part that I remove can be defective or the second part, right? So I said or, and because I said or, I have to add these two, right? So this is equal to probability of first defective and second non-defective plus probability of first non-defective and second defective, right? So now basically, once I broke this down, I can calculate both of these terms similar to the previous case, right? So this is going to be first defective and second non-defective. That's going to be, so first defective is, I want my first part to be defective. So that's 50 divided by 850. And now I want the second to be non-defective. So the second will be among the 800 parts divided by 849 plus. Now I want the first to be non-defective. So that's 800 divided by 850 times second defective. So that's 50 divided by 849, right? And if you look at these two terms are the same thing. The denominator is the same thing. And the numerator is also 50 times 800, 50 times 800, right? Same thing. So it's basically 2 times that. So it's 2 times 50 times 800 divided by 850 times 849, right? Okay. So I calculated f of 1, that's the answer. And the final f that I need to calculate is f of 2, which is P of x equal to 2. This one only has one term. I don't need to add things anymore, right? Because for both of them to be defective, I only have one option, first defective and second defective. And that is going to be 50 divided by 850, first defective times second defective, 49 divided by 849, right? So that's it. I have f of f of 0, I have f of 1, and I have f of 2. I have everything that I wanted. So yeah, question?
Yeah, is it possible to explain how we got f of like the calculation for f of 1 from the previous slide?
So this one?
Yeah.
Yeah, so f of 1 is p of x equal to 1, right? So basically, I only have one defective part out of the two. So when I have one defective part, I have two options. Either the first part is defective or the second part is defective, right? So because I said either or, it's a plus. So I add up the two probabilities. And now first defective and second non-defective. So first defective, because the first part has to be one of the 50 out of 850. And then second non-defective. So for the second part, I have 849 parts left out of a total of 800 non-defective ones, because remember, the second one has to be non-defective, right? So this is this term. So this is this term. And then I want basically the second to be non-defective. Sorry, the first to be non-defective. So the first non-defective, the first part has to be one of the 800 out of 850. And then second defective. When I pick the second one, I have 849 parts left. And I have a total of 50 defective parts. So this is the second term here. Was this your question?
Yep. Thank you so much.
Yeah, sure. And these two are equal, right? So these two terms are equal. Because of that, I simply write 2 times 1 of them, right? So, I mean, these three numbers are summarized in the next slide. So as we could expect, right? When I have a bag full of 800 non-defective and only 50 defective, when I pick two parts, the most probable outcome is that both of them are non-defective, right? So it's always good after you solve a problem to do like a sanity check to make sure, you know, things still make sense. So when I pick two parts, there's 88% chance, more than 88% chance that both of them are non-defective. Both of them are among the 800, right? And the probability of both of them being among these 50 is very low, right? It's like 0.3%. So basically we have here, these are basically fs, right? So this is f of 0, this is f of 1, and this is f of 2, right? So to calculate CMF, a cumulative mass function, remember f of, for example, 1 is equal to f of 0 plus f of 1, right? And so forth, right? F of 0 is equal to f of 0, right? Because there's nothing before 0 to add up. And then f of 2 is cumulative, so that's equal to f of 0 plus f of 1 plus f of 2, right? So it's basically solved. To basically find CMF, all we need to do is to add up these numbers. So these are the answers, right? So f of 0 is the same answer, f of 1 is 0.99, and f of 2 always must be 1, right? Because the final number is one of the axioms of probability. It must be 1, or otherwise you have made a mistake somewhere, right? And this is the answer to the good question that came off, is X for CMF continuous or discrete? As we see here, X is continuous, right? So X can be like 0.5, can be, you know, any number. But we see that this function is discontinuous, right? Because we are looking at discrete random variables. So anywhere, you know, we have a probability, we have a jump in the value of the function. And we also see that it's monotonically increasing, right? It's always either constant or it's going up. Any questions?
Sir, I have a question.
Sure.
Since the number of defective parts in this example that we can get is maximally 2, why does the function seems to be continuous after x equals 2? Shouldn't there just be a dot?
Yeah, so basically the reason that x is constant after 2 is that we are only selecting 2 parts. We are not, so you're right, you know, we have a total of 850 total parts, right? That's a very good question. But the problem statement says that we are picking 2 parts. We are not picking 10 parts. We are not picking all of the 850 parts. We are only picking 2 parts, right? So x can only be 3 different numbers, 0, 1, or 2.
Yes.
Was that the question?
Yes.
Yeah, okay, very good. Other questions? Okay, so there's more people that joined, so let me. All right. Okay. So I wanted everybody to join to talk about some logistics. So you have to form groups for your project by January 28. The TA already sent you an email to form groups. So you write basically your name in that in the Excel sheet that he shared with you, and you have to write a project proposal and send it to the POD after you form your group, right? And basically, you should read the project handout to find out what you should write in the project proposal. And the deadline to submit the project proposal is 1 week before the midterm exam. So when you submit the proposal, either your proposal will be accepted or rejected. It will not be graded. And if you get a rejected proposal, you know, you're just asked to, you know, like he will give you comments to improve your proposal and then submit your proposal again. This is just to make sure that, you know, you don't doubt your project halfway through, right? You make sure that your project is acceptable for this course. So this is a service to you. You shouldn't be worried about the project proposal. And of course, you have to submit your proposal, because if you don't submit your proposal, we will not let you do the project. So this submitting the proposal is a prerequisite to doing the project. And it's a bit too early to talk about the proposal. Very soon, starting from week 5, the POD, you know, will be available to answer your questions about the project. The reason I'm talking about it now is just to, you know, is to basically for you guys to start thinking about this. Yeah, go ahead. There's a question.
Is it one proposal per team?
Yeah, one proposal. Yeah, so one proposal per team, and all the members of the team will receive the same grade.
Okay, thank you.
Yeah, sure. And remember that you have to submit this basically originality form with your project, right? But the actual project due date is later. It's the last day of the tutorial. So basically, you don't hand it in during the class. You basically submit it during the last tutorial, and I encourage you to submit it electronically, so you don't really need to print anything. But it's much later, in a few months. Other questions? Okay. And I already mentioned the midterm class, midterm exam, sorry. So the reason I'm mentioning this is that so that you guys start making sure that you have an ENCS approved calculator, because the midterm will be in person during class, and I will not let you borrow somebody else's calculator if you don't have one. And your calculator must be ENCS approved, and we will give you the crib sheet. So it basically has all of the equations that you need. Any questions? Okay. So now we start talking about a very important and very interesting concept, and that's the concept of mean or expected value. All of you guys are, I'm sure, are familiar with this concept. but we will try to make it concrete and basically crystal clear what is the concept of mean or expected value, right? So it's denoted as E, expected value, E of X. Remember, X is a random variable, right? And the equation for that is sigma X, F of X, right? And F is the probability, right? Probability of getting X, right? So let's look at an example. We roll a die and X is the number of times, X is the number on the top, right? So basically in this experiment, we roll a die one time. So X can be 1 or 2 or 3 or 4 or 5 or 6, right? Because these are the numbers on a die, right? And probability of each one of them is, so probability of X equal to 1 is probability of X equal to 2, ... is equal to probability of X equal to 6. All of them have a probability of 1 divided by 6, right? So we want to know what's the expected value of X. Does anybody, can anybody guess what is E of X? So E of X means like the mean number that we get, right? So obviously E of X is not going to be 1 because 1, you know, it's not the average number that we get when we roll a die, right? It's also not going to be 6 because 6 is an extreme case, right? Is an at the end of the spectrum, right? So we get the expected value, you know, like somewhere in the middle, right? So let's calculate it. So basically, according to the equation, E of X is also denoted as mu, is sigma X F of X, right? So that means that let's write down X F of X, right? And here X is from 1 to 6. So that is 1 times F of 1 plus 2 times F of 2 plus ... plus 6 times F of 6, right? But remember, as we said up here, so these are Fs, right? So this is F of 1 is equal to F of 2 is equal to ... is equal to 1 over 6. All of the Fs are 1 over 6, right? So this term is equal to, so these are all 1 over 6, so we can factor them out. Sorry. So it's 1 over 6 times 1 plus 2 plus ... plus 6, right? And if you do the math, this is, then you get 3.5, right? So when we roll a die, the expected value of X is 3.5, right? So remember, expected value doesn't mean that it's most likely to get this number. In fact, in this example, the probability of getting 3.5 is 0, right? Because there's no number on the die that says 3.5, right? This is the average that we get, right? So again, I repeat that because that's a very important statement. E of X doesn't mean that probability of getting X is the highest, right? Because in this case, probability of getting any number is 1 over 6. So in this example, 1 is as likely as 2, as likely as 3, and so forth, right? So the outcome of X basically has a, we call this a uniform probability. So all of the probabilities of getting any number is constant, right? E of X means in average, what do I get for X, right? So for example, if I repeat the die many, many times and average the results, what do I get, right? So the answer is 3.5. That's the average number that we expect to get when we roll a die.
Professor?
Yeah.
Can you please go to the previous slide for a second?
Yeah, sure.
The 1 over 6 before the brackets, that's the shared F of 1, F of 2, F of 3, and F of 4 till F of 6, yeah?
Yeah.
Okay, thank you.
Yeah, sure. Other questions?
Just quickly,
Sure.
F of all these numbers is shared because this is an independent experiment, yes?
No. So these, yeah, so basically, in this experiment, I'm only doing the experiment one time. So, right, that means that I'm only rolling the die once, right? So independence is defined when I'm doing multiple experiments, right? So I'm not rolling the die 2 times. Yes, you're right. If I was rolling the die 2 times, the outcome of the first experiment and the second experiment were independent from each other. But I'm only rolling a die 1 time, right? And X is the number that I get on the die. So X can be 1 all the way to 6. So independence is only, defined when when I have, for example, multiple experiments, right? Here, I'm only doing that experiment once.
Okay, I get you. Okay, thank you.
Yeah, so if you like to think about, like the concepts that we spoke, you can think of X equal to 1 as one event. So if you like to think of it that way, so, oops, sorry. I think I lost it. Yeah, so basically you can think of, in this experiment, you can think of set A as X equal to 1, and then set B as X equal to 2, and then all the way A, B, C, D, E, F. So F, this is 6th set, that's X equal to 6, right? So basically, these are the different outcomes that I can get. Now, A and B are mutually exclusive. So A and B cannot happen together, right? Because we cannot get a 1 and a 2 at the same time. So all of these events are mutually exclusive, right? So if this is my sample space, then this is A, this is B, all the way to F. These are mutually exclusive, right? So that means that my sample space contains 1, 2, all the way to 6. Okay, any questions? Right, seems none. So yeah, so this is the computation that we just did. Expected value is 3.5. And if we basically assume that f of x is the probability mass function of the loading on a beam, then E of x is the balance point, right? So in other words, if I assume that I have a mass at 1, and this mass is 1/6 of a kilo, right? And another mass at 2 meter, and this mass is 1/6 kilo, right? Another mass at 3 meter, and this mass is also 1/6 kilo. Another mass at 4 meter, and this is also 1/6 kilo. And another mass at 5 meter, this one is 1/6 kilo. Another mass at 6 meter, this one is also 1/6 kilo. Then the expected value is the basically balance point right here, right? So that's the concept of the expected value or the mean. All right, so another example, we are flipping a coin, and let's say you're playing a game with your friend, right? You flip a coin, you win $1 if it's head, you win nothing if it's tails, right? X is the amount that you win. What is X? So to calculate X, we will say, okay, E of X, I follow the definition, is sigma X f of X, right? So what values, so I win $1 if it's head, right? So here my, yeah, so I can't really, so to solve this, actually, I need another equation that I'm going to introduce later. So let's not answer it this way. So the way I'm going to answer it is that here I have only 2 outcomes, right? So with the probability of 1/2, I'm going to get heads, and with the probability of 1/2, I'm going to get tails, right? So E of X is going to be sigma X f of X, right? And then in this case, if it's heads, I'm going to win $1. And if it's tails, I'm going to win $0, right? So that's equal to 1 times the probability of winning that $1, 1/2, plus 0 times probability of 1/2, right? And that's $0.50, right? And that is intuitive, right? When you play this game, you're expected to win $0.50. All right, so we will talk about expected value all the time in this course, right? And it's also a very important concept in your life, right? When you make an investment, you know, when you do anything basically in your life, you have to have the notion, you have to know what's the notion of expected value, right? Of your return, for example, because that's a very important concept. The next important concept that we cover is called variance, right? So first we talk about the equation, and later on we see what's the meaning of this one. So variance is defined as x minus mean to the power 2 times, see what time it is, times the probability, right? So that's the definition of the variance. Now we can expand this. So this is the expansion. And then I can basically multiply all of these by f of x, right? So this is x squared f of x, this f of x, the middle term, and the final term, right? And since this is constant, this comes out of the sigma, right? But remember here that this term, sigma x f of x that I see here, that's the definition of mu, right? Remember mu was defined as e of x was sigma x f of x, right? So here, instead of this term, I'm going to enter mu. So this becomes minus 2 times mu squared. So this and this cancel, and at the end I get this equation, right? So these two are equal to each other. The one at the top is the definition. The other one is a computational formula. These two are always equal, right? So it doesn't matter which one you use. Usually the one in the bottom is easier to compute, right? So we usually use this one to compute variance. Okay, so let's look at an example to see basically to make sense of this concept, right? So in the previous example 3.4, there's a chance that a bit is transmitted through a digital transmission channel, but it's received in error, right? X is the number of bits received in error in the next 4 transmissions. So I have a total of 4 transmissions, right? So X can be 0, basically 0 bits in error, all the way to 4, all of the bits received in error, right? So for now, assume that I know these probabilities, right? So don't worry about how I computed them. If you have really mastered the material so far, the solution to this is quite similar to the previous, like you can actually compute these using the concepts that we already know, but we are going to introduce equations later on in this chapter to solve these really easily using those equations. So for now, you can not worry at all about computing these. Very soon, in a week, in 2 weeks, computing these will be the easiest thing for you, right? So assume that somehow we computed this, like 0 bit transmitted in error, 1 bit transmitted in error, and so forth, right? So in this case, these are provided by the question, but we don't really need them. We can compute them. So basically, to calculate, so the question is, this question doesn't concern how to compute these. This question concerns calculating the mean and variance of the number of bits in error, right? So the question is asking, what's the average number of bits that we receive in error, right? So X is between 0 to 4. So the final answer that we get is going to be a number between 0 to 4 as the mean. And also the question wants the variance, right? So since the equation is X times f of X, it makes sense to tabulate the results. So X can be 0 to 4. And basically, I wrote all of these numbers in this table, right? All the way to P of X equal to 4, which is this number, right? Now, what I'm going to do is that I'm going to calculate X times f of X right? Because I need that for computing the mean. So all I do here is multiply this number by 0, right? This number by 1, it's the same number, and so forth, right? This number by 2, it's this number, right? So now that I basically create this column to calculate the mean, all I need to do is to add up these 5 numbers, right? And actually 4 numbers, because one of them is 0. So if we add up these 4 numbers, I get the mean, right? So remember that, so here we have to calculate the mean. See, so the mean is actually 0.4, right? So if I do that, if I do some of these numbers, mean is going to be sigma x f of x. That means that the summation of these 5 numbers. And if I do that, the number that I'm going to get is going to be 0.4, right? So now remember that the definition of the variance was sigma x minus mean to the power 2 times f of x, right? So because of that, I'm also going to compute x minus mean. So the mean is 0.4 to the power 2, right? So that means 0 minus 0.4 to the power 2. So 0 minus 0.4 to the power 2 is going to be 0.16, because 4 times 4 is 16, right? Next, same for this one, right? So here, this number is basically 1 minus 0.4 to the power 2. That number is this number, 0.36. And so forth, right? So I calculate all of these guys. And to compute the variance, remember I have to multiply this by f of x. So I multiply all of these numbers by f of x, which was here. So 0.16 times 0.65 is 0.1, right? And so forth. So now to calculate the variance, all I need to do is to add up these numbers, right? So if I add up all of these numbers, all of these 5 numbers, I will get the variance. Now remember, there were 2 equations for calculating variance, this one and also this one, right? So since this is the first example, just to check, we are going to compute variance using both equations. We never do that. It's just, since it's the first time, we like to do that to make sure that they give us the same answer, right? So in the last column, I'm trying to use the second equation, which said this is equal to sigma x squared f of x minus mean to the power 2, right? So here I'm computing x squared times f of x in this column. So 0 squared times f of x is 0, and so forth, right? So the rest of the computations are here. So if I add up all of these numbers, I get 0.36. So this is variance, right? I could also basically add up these numbers, right? As I said in the previous slide, so sigma x2 f of x minus mu to the power 2. So if I add up these guys, the number that I get is 0.52. So that is 0.52 minus mu is 0.4 to the power 2, right? And if you do this computation, again, you will end up with 0.36, right? Same number. So we computed variance using 2 different methods. Just once, we never do that again. Just to make sure we get the same answer. Any questions?
Yes, Professor, just one question quickly.
Yeah.
I know you said don't bother calculating p of x equals 0, but like out of curiosity, like wouldn't they have to like provide us with the chance that an error is received so we can calculate p of x equals 0 with the methods we've learned?
Yeah. So when you were actually when I was talking about it, I realized that to compute these, we need to know the chance of getting 1 bit in error. You're absolutely right. That's an excellent question, and that chance is actually the chance of getting 1 bit in error. Actually, we can get that very easily from this number, because this is the chance of getting 4 bits in error, and that's obviously 10 to the power minus 4. So in this question, the chance of getting 1 bit in error is Can you say what that is?
Is that number
know?
divided by 4?
No, that's the fourth square root of that number.
Oh, okay, yes.
So 1 bit in error is 0.1. So don't worry at all if you have no clue about why this is the fourth root of this number. It's because we haven't talked about it. So we will talk about it next week.
Okay, thank you.
Yeah, sure. But yeah, you're right. We can't really compute these probabilities not knowing, what's the probability of 1 bit in error. Other questions? I'm
Yes,
very
sir.
happy you asked that question because that means that you're listening carefully. Yeah, go ahead.
I have like a general question. Could you please explain the meaning of variance again? What does it mean?
Yeah. So that's another great question because I never explained variance, right? So for now, don't worry about it. Just for now, just think of it as something that we compute. Later on, I will explain what it means. Basically, as the word suggests, variance means how much variability we can have, right? So the larger the variance, it means so basically mean means average, right?
Yes.
So in this case, mean is 0.4. That means that yes, the number of bits in error can be 0, or it can be very high, it can be 4. But in average, we expect 0.4 bits in error because remember, if you look here, the chance of getting 4 bits in error is quite low, right? So it means that in average, we have only even less than half a bit in error, right? So that's the meaning of mean. That's quite easy to understand. Now the variance basically means how much variability you can have, right? So that means that yes, the mean is 0.4, but is it likely that you get 4 bits in error? Is it likely that you get 3 bits in error, which is far from 0.4? Or all of the, basically, if you do this experiment, the bits that you receive in error are very close to 0.4, for example, 0.44 or 0.41 and so forth, right? So variance basically indicates variability, like how much variability you have around your mean.
Okay.
So don't worry at all if what I said didn't make any sense, because we will talk about it in detail later on.
Oh, I think
yeah.
Sorry, I didn't mean to.
Yeah, go ahead. No, go ahead.
I think I do understand. So if we were to draw a bell curve of all the possible outcomes, variance would probably define how wide that bell curve is.
Exactly. Yes,
But,
you're absolutely right.
What I wanted to know, since when I asked the question, is variance the same as standard deviation? Because that I know from grading systems, but they're different, right? Okay.
Yeah, so they are a little bit different. So variance, variance is standard deviation, STD to the power 2. So standard deviation is the square root of variance.
Okay. Thank you, sir.
Yeah, sure. And you're right. What you said is absolutely right. If we draw we will talk about Gaussian, distributions. So if we draw a Gaussian, variance tells us how wide this thing is, right? So the larger the variance, the wider the Gaussian.
Thank you so much.
Yeah. Other questions? All right. So we can move on. So now we talk about another very important concept, and that's the concept of expected value of a function, right? So what is expected value of a function of a random variable? So before, the equation that we saw was expected value of x, right? And that was sigma x f of x, right? So what about expected value of a function of x, right? So to compute that, the equation for that is h of x, sigma h of x times f of x, right? And note that this is not f of h of x, this is simply f of x. This is called the law of unconscious statistician, or LOTEST, right? Because in reality, what you have to do to compute h of x is you have to define h of x as a new random variable y, because x is a random variable, any function of x is a random variable, so we define this as y, and therefore e of y is sigma y f of y, right? According to the definition, right? So obviously, this equation is different because this equation that I provided here, it simply says that E of y is equal to sigma y times f of x, not f of y, right? So there's a proof that these two are equal, right? And the reason this is called law of unconscious statistician is that many statisticians use this equation without knowing that this is not the definition. There's a proof that these two are equal, right? But for the sake of this course, you can always use this equation, right? You don't need to use the original one, right? Any questions? Okay, so let's look at an example to see basically whether this makes sense. So the first example that I'm going to give you is this equation is correct for any h, right? So I'm going to set h as x minus mean to the power 2, right? And mean is called is defined as the expected value, right? So excuse me. So in this case, if I replace h with x minus mean to the power 2, then if you look at this equation, this becomes variance, right? So if I do this, then E of h becomes sigma x minus mean to the power 2 times f of x. And that's the definition of variance, right? So variance is simply expected value of x minus mean to the power 2, right? So, that wasn't a very intuitive example. Let's look at one intuitive example to see what's the meaning of E of h of x, right? So assume that we have the PMF, probability mass function. So probability of x equal to 0 is this number. It's the same example as before, right? The 4 bits transmitted in error, right? Probability of having all 4 bits transmitted in error is very low, right? And we basically want x is the number of bits in error, right? What's the expected value of the square of the number of bits in error, right? So we don't want expected value of the number of bits in error. We want expected value of square of the number of bits in error, right? So that means that what we are interested in is expected value of x squared, right? So to compute that, I'm going to use basically, so therefore I need E of h of x, which is sigma h of x, f of x, right? And that is equal to sigma x squared f of x, right? So all I need to do is that I need to compute x squared times f of x, right? So that is going to be equal to 0 to the power 2 times 0.65 plus 1 to the power 2 times 0.29 plus 2 to the power 2 times times 0.48 plus ... right? So all of these numbers to the power 2 times their probability. Any questions? Okay.
So it's just really the law of unconscious statisticians is just really replacing the x with whatever function is needed.
Exactly. Yes, you're
Okay.
absolutely right. Yeah.
Okay. Thank you.
So yeah, sure. So basically, if I go back, yeah. So the original equation was E of x is equal to sigma x f of x. Now the new equation, law of unconscious statistician, is if you replace x with h of x, here x will be replaced by h of x, but f remains the same, right? It's still f. So yeah, you're right. So the final answer that we get is 0.52, right? So that's the expected value of the number of square of the number of bits in error. Okay. So before I go to the next slide, I'd like to give you another example. So let me. Okay. All right. So let's try to do another example. So here the example is the following. We roll a die, right? Let's say you're playing a game, you roll a die, you win. Let's say you're a casino and you're playing this game, you win. Oh. You win x squared if x comes up, right? So for example, if you get 6, you win $36, right? So we want to calculate in average how much are you expected to win, right? In other words, what is E of X, right? So to solve this, I'm going to say, sorry, E of X squared, right? So I'm going to say E of X squared is equal to sigma X squared times F of X, right? And that is going to be 1 to the power 2 times 1 over 6 plus 2 to the power 2 times 1 over 6 plus plus 6 to the power 2 times 1 over 6, right? So I can factor out all of the 1 over 6s. So that's 1 over 6 times 1 plus 2 to the power 2 plus plus 6 to the power 2, right? So that's the answer. That's basically in average how much you win playing this game. Any questions? All right. So for example, let's say you're playing this game at a casino, right? And the casino owner tells you that, you know, you can play this game, but in order to play this game, you have to buy this token, right? And this token that you have to buy is $20, right? The question is, would you play this game or no? So like if you play this game, you know, you can win $36, right? Or you can win only $1 if you get a 1, right? So the question is, would you pay $20 to play this game? Any answers? So that will depend on whether this E of X that we computed is more than $20 or less than $20, right? I don't really know what is E of X. Can someone please compute it? It's not too difficult. So it's, I don't have a calculator handy. So it's simply the summation of these numbers divided by 6. So let me try to do it. If somebody does it before me, great, let me know. So
Yeah, somebody's in the chat said, but it's 15.16.
15.1, thank you. All right. Oh, I think I lost everything. So yeah, so basically E of X squared is 15.1. Yeah, 15.1. So obviously you lose money if you play this game because E of X squared in average, you're expected to win $15, but you're expected to pay $20 to play this game. So in average, you lose about $5 if you play this game, right? And by the way, that's how casinos design their games. in average, your expected value of return is always less than what the money that you put in, right? So statistically, you're always expected to lose money whenever you play. Same with lottery tickets. You're always expected to lose money. That's why lottery companies and casinos make money, right? Because in average, they always win. Any questions? Okay. So the rest of this chapter concerns with computing, basically giving you equations for different types of distributions, right? So the first distribution is a uniform distribution, right? So here I have n outcomes, right, with equal probabilities. Since the probabilities are equal, the chance of each one of them is 1 divided by n, right? And you can see like one immediate example is my favorite example of rolling a die, right? So x1 is 1, x2 is 2, all the way to xn, which is 6. And the chance of each one of them is 1 divided by 6, right? So for this case, for the case of uniform distribution, the average value is basically provided by this equation. So if my values are changing from A to B, then f of x is 1 divided by b minus a plus 1, and the expected value is a plus b divided by 2, right? So this is quite intuitive. If my values are changing from A to B, and all of them are equally likely, therefore the expected value is right in the middle, right? It's the summation of these two divided by 2. Now, the other number, so let's give an example. So if I'm rolling a die, then A is 1, A plus 1 is 2, and then B is 6, right? For the case of rolling a die, right? So if I use this equation, I'm going to get 1 divided by B, which is 6, minus A, which is 1, plus 1, right? So I simply get 1 divided by 6. So this equation is the simplest equation you can imagine, right? So it just gives you the chance of basically getting every outcome. Any questions?
Yeah, I just had a small question quickly. For the mean here, the discrete uniform distribution, this is a mean, it's not a median, yeah? Because
yeah,
for a
this is the
second I
mean.
thought this. Okay.
Yeah, this is the mean.
For a second I thought it was a median, and it didn't make sense to me.
Yeah,
Okay,
this is the
thank
mean
you.
average. Yeah, so we will very briefly talk about median in this course, but we always talk about mean and variance in this course. We don't really talk about median, sorry. So always we talk about average or mean, not about median. And by the way, this equation, right? We can simply prove this equation. This equation is not a difficult equation to prove. And in fact, I do encourage you to prove it because it's a very good exercise. So E of x is sigma x f of x, right? So remember all of the, and we have f of x here, right? So that means that sigma x times 1 divided by b minus a plus 1, right? So this is a constant, comes out of the sigma. So that's 1 over b minus a plus 1 times sigma x, right? So what is sigma x? It's basically a plus 1 plus dot 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 plus b, right? So if you do the math, everything cancels out, and at the end you get a plus b divided by 2, right? So this is a very easy equation to prove, and I do encourage you to prove it. I just basically wrote the outline here how to do that. So it's basically the proof for this is exactly what we did for, remember for rolling a die, we calculated the mean, right? And for example, in that equation, what we get here, B is 6, A is 1. So if we use this equation, we get 6 plus 1, which is 7 divided by 2, and that is 3.5, right? The same number that we got before. But we got this number without this equation, right? So the way we got this number was basically this proof. And you can see the probability comes out of the sigma. It's the same thing we did. We factor out 1 divided by 6. Okay, so it's 1:30. Thank you guys very much. Have a nice weekend.
You too. Thank you.
Sir?
Thank you. Have a good weekend, sir.
Yeah, I'm going to stop recording. If you have any questions, you can ask.